Hello everyone, welcome to my programming club. Today we will be solving another daily Leetcode problem, and the problem's name is perfect squares. So the given statement goes like this: given an integer n, return the least number of perfect square numbers that sum to n. Okay, so a perfect square is an integer that is the square of an integer. Okay. In other words, it is the product of some integer with itself. For example, 1, 4, 9 and 16 are perfect squares, while 3 and 11 are not. Okay. So you have to return how many number of perfect square numbers will be required to form a particular sum. Okay, this is the target sum, or let's say the target value. So you should tell how many perfect squares less than this particular sum are required so that they can sum up to this particular number. So the number of perfect square numbers that are lesser than this particular 12 is 1, 4 and 9. So we have to consider only these numbers, since these numbers are perfect squares, and uh, it is lesser than this n. All of these are lesser than n. Okay, so you should be telling that what is the minimum number of numbers that can add to this 12. So one way of doing this is you take 112 times. Another way can be for 3 times. Okay, so there are several combinations possible. Among those combinations, only this combination gives you the minimum number of times. Okay, so answer will be 3 times. Okay, so let's have a look at the constraints also. So the length of, or the order of this particular target sum, or n, will be 10 raised to power 4. Okay, so there is a mathematical, you can consider it as a fact, or uh, just as of now we'll consider it as a fact that the number of perfect square numbers lesser than or equal to a particular number, let's say n, is equal to square root of n, or you can say sqrt of n. Okay, so if you see square root of 12, let's see what will be the square root of 12. So it's 3 point something. Okay, so if you take our integer value only, so it is 3, so it should be less than equal to 3 number of numbers that are perfect square and less than n. So indeed these are 3 numbers only. If let's say you consider 25, then you may add one extra number, which is 16, two extra number actually, which is 16 and 25. So if you do square root of 25, it will be 5. So if you see that there are 5 numbers only. Okay, so this is a fact that I thought to tell you in case you do not know. This will be used in solving this particular problem. Now let's see how we'll be applying a brute force approach first here. Then we'll be seeing that whether that brute force approach is sufficient to solve this particular problem or not. Okay, so let's consider a brute force approach. In brute force approach, right now, let's say we are not allowed to repeat the numbers for now for simplicity. It is for checking whether this brute force approach is sufficient to solve this problem or not. So every number, let's say we are required to form some combinations. Let's say this is combination 1, combination 2. So in all there can be some combinations, just like there were these two combinations possible. Others were possible also, but 1 repeated 12 times and 4 repeated 3 times. So both of these were summing up to 12. Okay, so these are combinations. You can call this combination 1 and combination 2. So for every number that is a perfect square and less than your target value, let's say target value is given something 12. So every number there will be two options. Either you will be taking it into the combination or you will be rejecting it and not taking it into the combination. Okay, and depending upon what combination you have formed, you will see whether this combination is summing up to your target. If this is the case, then you will see how many numbers are there in that combination. So you will be generating all the possible combinations. Okay, all possible combinations. So in all, how many number of combinations will be generated? 2 into 2 into 2. This will be repeated square root of target times. Okay, and the upper bound on target was 10 raised to power 4. Okay, so if you take 10 raised to power 4 square root, it will be 10 raised to power 2, which is nothing but 100. So overall the number of operations that will be required will be order of 2 raised to power 100. Okay, to generate all possible combinations. So these number of operations are very much greater than the operations limit. This is the ops limit, 10 raised to power 8 ops limit. If let's say the number of operations required by your program or solution to solve a particular program exceeds or become equal to this operation limit, then you may get a TLE and your solution will not be accepted. So here you will be getting a TLE, time limit exceeded, and your solution will not be accepted. So we have to do some optimizations in this particular brute force approach. So optimizations are required. Okay, so what optimizations should we do in order to get this particular solution accepted? Okay, so let's consider a scenario that 4 plus 4 plus 4. Okay, till here your sum was 4, then it was 8, then it was 12. Okay, this is sum values, or let's call it running sum values. Okay, running sum values. Let's say this is a combination. Let's call this combination 1, and there is another combination 2. Let's say it is. Then let's say till here everything is same with respect to combination 1, and after that let's say there are 4 ones. Okay, so if you see running some values for this particular one, they will be 4, 8, 9, 10, 11 and 12. Okay, so if you see, these running sum values are repeated in both of the combinations. Okay, so let's say if you knew that how many combinations will be required to form 8. Okay, how many numbers will be required in minimum to form 8? Okay, how many perfect square numbers required to form 8? Then you need not have to do recomputations here, since these two subproblems are overlapping and you will be doing extra work here. So if you knew this particular result, then you would have avoided some extra work, and if you are not storing it somewhere, then you will sure be doing extra work here. Okay, so this is the first observation regarding the problem, that it is following a property of a problem which is overlapping subproblems and which is leading us to do extra work. Okay, those of you who are new to this particular property, I'll be providing a link of an article where you can read about it, and you will be understanding uh, in a better way how these overlapping subproblems affect the overall runtime complexity. Okay, so it will lead us to do some extra work, and that's why we can save its the intermediate result somewhere, and we will be avoiding extra work. So another property that this particular problem is satisfying is, let's say you are required to know how many numbers are there in minimum which will add up to 12. Okay, so you should be knowing the answers for how many numbers are there which would be adding for 8, if let's say you were selecting 4. Okay, or other way of saying that is, solution of bigger subproblems in this particular problem can be derived from solution of smaller subproblems. Let's call this solution 1, solution 2 and solution 3. So subproblem solutions can be combined and they can be used to derive the solution of bigger subproblem. Okay, so this is a property that is being satisfied here. So this particular property is called optimal substructure. When these two properties are satisfied by a problem, I'll also be providing link for this one also. Okay, so for those of you who do not know what this particular property is, you will be able to understand in a much clearer way if you visit this link of an article. So when these two properties are satisfied, an optimization technique can be applied here, which is called dynamic programming. Okay, so what we do in dynamic programming is, it is not just optimization or brute force. When you see a overlapping, whenever you see a sub problem, you will store its result. Okay, and whenever this sub problems occurs again, okay, in some another combination or somewhere else while you are recursing, then you will be using that stored result to avoid extra work. Okay, so what dynamic programming does is, first of all, it will store all intermediate states, or store results for all states that are there. So if states, okay, and use those results to avoid extra work. In case of overlapping subproblems, okay, this is just a single step. It is a twofold process, and other than storing the results for all states that are there, it will use the solutions of or state results of smaller states to form solution of bigger states. Okay, so this is in nutshell what dynamic programming is. I'll be also providing a link for this particular technique also, and you can check this link, and there will be an article explaining what dynamic programming is. So in this particular problem, how we will be applying dynamic programming? To apply dynamic programming over a particular problem, first of all, what should you be doing is you will be seeing how how many state variables will be required to define a state in a problem. Okay, so we'll be seeing how many state variables will be required. If you carefully observe, only a single state variable is required, which is running sum. Okay, so let's say your current variable current value of running sum is 12, then how could you have landed upon 12? Okay, you will consider all possible options that are out there. By all possible options I mean 1, 4 and 9, that are perfect squares which are lesser than 12, and among these perfect squares we will subtract these perfect squares from 12. So if you subtract 9 from 12, it will be 3. So since 3 is not a perfect square, but it it can be a number that can lead us to 12. If you subtract 4, then it will be 8. Okay, and if it you subtract 1, then it will be 11. Okay, so this is another these three are another subproblems in themselves. Okay, these three are subproblems. Okay, and this is also a subproblem, or you can say a bigger subproblem than these. So this is your current state. Okay, and these can be your previous states which could have led us to 12. Okay, so these are your previous states. Okay, so you will be able to observe that only one state variable is required, which is the value of uh, running sum. Okay, or you can say value of current value of target. Okay, you will be varying your target from 1 to n. Okay, so initially your target is equal to n, so all of the values from 1 to n will be considered as your states. So since there is only one state variable, so how many number of dimensions of dynamic programming will be required to store, only one DDP will be required. Okay, so a 1D array would be sufficient to store the results of all the intermediate states. Okay, these are states. So let's see how we'll be applying dynamic programming here. For all the states from 1 to n, you will pick a current state. Okay, and for this current state you will be seeing what are the previous states possible. Okay, and you will be taking contributions from previous states and adding 1 to them. Okay, so if you observe here also, only one jump was required from 3 to go to 12, which was adding 9. Okay, and if you are at 11 it would be adding 1, and if you are at 8 and it would be adding 4. So you see only one step was required. So if you know the answer for 8, then it will be answer for 8 plus 1. Okay, similarly if you know the answer for 11, then it will be answer for 11 plus 1. Here also it will be answer for 3 plus 1. Okay, so these are the contributions of previous states that are there. So what you will be doing is, let's call number required or squares required for a particular number. Let's say this is your current state, then it will be nothing but minimum of 1 plus minimum of previous states contributions. Okay, so looks like we are having a state transition equation here. Okay, so these previous states will be nothing but current state minus all possible will be looping for all possible perfect squares lesser than the current state, less than current state value. Okay, let's see the implementation, then there will be it will be more clear to you how this state transition equation is working. Okay, so the implementation part is quite concise here. Okay, for initially you will consider that for every number that is there, for every possible state, state value, maximum number of infinite number of or let's say maximum int value number of numbers, perfect square numbers will be required to add up to that state. Okay, for every possible state let's consider infinite number of perfect square numbers required, or these much number of perfect square numbers are required. Since int max is very much greater than this 10 raised to power 4, that's why we have taken this limit. So it will, you can say roughly it will be infinity for this particular problem. Okay, for every state value, let's consider infinite number of perfect square numbers required. But you will see that if let's say this n would have been 0, then there are 0 numbers that are required to make up a sum equal to 0. How many numbers are required there? Okay, so let's say this was your target sum 0. So in all, 0 numbers are required, 0 perfect square numbers lesser than target are required. Okay, so you will initialize numbers required for target sum equal to 0 to 0. Initialize perfect square number of perfect square numbers lesser than 0 required to sum up to 0 as 0. Okay, so after that, for every state possible, you will be taking contributions from the previous states, and you will be taking minimum of those contributions and adding 1 to them. Okay, here state is nothing but current value of target, or say n. Okay, it will be ranging from 1 to n. So for current number, what would have been your previous number? All the perfect squares that are lesser than the current number will be the previous numbers that would be possible. Okay, so you will be updating your squares required. Okay, and you will be taking minimum of these two, current value of your square required, and this is contribution from previous number. Okay, previous state contribution, you can say. Okay, and instead of number you can say current number. Okay, so at last you will be returning your number of minimum squares required for making up sum equal to n. So that is how we will be solving this particular problem. If you are still having any doubts or any queries in general, then please feel free to ask them in the comment section. Thank you for watching. Have a great day ahead.